So good morning, everyone. It is my great pleasure to welcome you for this last seminar of the Good Vibrations seminar series. Just before I give the floor to Masao, I just want to say a couple of words. So we've been very happy to organize this seminar series, and we thought it was quite useful to counterbalance the lack of meetings due to the pandemic. The last season, the third season, we thought that the second season at the end, we realized that there were maybe some conflicts with the summer conferences, that some speakers were actually offered talk at the two for the seminars and for the conferences, or sometimes that in the SUCs the SUCs were wondering if they would give seminars, give talks to speakers who had seminars before. So that was the reason why we kind of short-turned the third season so that it ends in March, so that it doesn't conflict with the conference season. And now this year we felt that that a lot of activity had resumed since the end of the pandemics, that a lot of meetings were organized at the end of the season, so that maybe it was the good time to end the seminar series right now. So I hope you all agree with this, and I just would like to thank very warmly the steering committee, who has made this initiative lively and interesting, and also who have helped me a lot with the organizing. A particular thank you to Antonio Garcia Hernandez for his help with the contact email, and to Dominic Bowman for. So it's time for me to leave the floor to Masao, who will introduce our last speaker of the season. And thank you very much again.
Okay, thank you, Rita. Hello, everybody. And let me introduce today's speaker very briefly. It is a great pleasure to invite Mr. Siddharth Dampal from Tata Institute of Fundamental Research in Mumbai, India, as the last speaker of the third season of the Good Vibration Seminar Series. And Siddharth started his PhD in 2018 under the supervision of Dr. Shravan Hanasoge, and will finish it soon in this July. He's an expert in the data analysis of oscillating stars based on machine learning, which is a powerful technique to analyze a large sample of stars, such as those observed by Corot, Kepler, TESS, and Plato. And in this seminar, we will listen to his latest result about Kepler red giants. So Siddharth, please start your presentation.
Thank you for the great introduction, Masao. I would also like to thank the steering committee for selecting me and giving me this opportunity to speak and showcase my work. So today I'll be speaking about ensemble astroseismology using deep learning. This is the outline of my talk. I'll first introduce astroseismology briefly. I will then talk about the method and simulations that I've used. I have organized my results into three categories: machine recovering the existing observations, machine discovering the deviations from existing observations, and machine discovering completely new observations. And then I'll conclude my talk. Astroseismology. All stars oscillate and they reveal themselves. We can understand the internal structure and internal dynamics by understanding these oscillations of the star. We observe light curve of the star, we take the Fourier transform and construct the power spectrum and extract resonant frequencies. By studying these resonant frequencies, we can understand many physical phenomena, like how angular momentum is transported from core to envelope. We can understand differential rotation in these stars. We can understand how strong magnetic fields are generated in these stars. We can model the stars better. We can understand the fundamental question of stellar evolution. So how does this seismic data look like? Primarily, there are two kinds of oscillations, P modes and G modes. P modes are pressure-driven oscillations. They dominantly exist in convective envelope of the star in sun-like stars. And P modes in the power spectrum are separated uniformly. For example, here I show you the oscillation power spectrum of a main sequence star. You can see the L equal to 0, L equal to 1, L equal to 2, and L equal to 3 P modes. And you can see that all these modes are separated uniformly. The distance between these two L equal to 0 modes, the frequency separation between them is large frequency separation, delta nu, which is more or less constant with frequency. Whereas G modes, these are buoyancy-driven oscillations. These have uniformly spaced periods, and they exist in radiative core of the star. These are not observed at the surface because of their very low amplitudes. They decay in this envelope, and they're not observed at the surface. And there are also something called mixed modes, which have both the characteristics of P modes and G modes. They oscillate as P modes in the envelope and G modes in the core of the star. Mixed modes can't be observed in this main sequence star, but as the star evolves, the P mode cavity and G mode cavity come closer, and we can observe these mixed modes. We can observe mixed modes in subgiants and red giant stars. You can see the oscillation power spectrum of a red giant star here, where we can see the dipole mixed modes, L equal to 1 mixed modes. So Kepler has 21,000 such red giants where we observe mixed modes, and only few of them have been successfully analyzed. To give the context, core rotation has been measured only up to 1100 stars out of this 21,000. This is mainly because of the complex analysis of this, involved analysis of this dipole mix. So this makes spectra complex, and it makes it harder to analyze. So the current technique, the current most accurate technique that analyzes spectra is NCMC. So the disadvantages of this method is that each star needs to be separated, analyzed separately, and it is computationally very expensive. It takes approximately a week to analyze a star. It requires a lot of human intervention. It requires visual inspection to perform NCMC. Coming to machine learning, we can analyze ensemble of stars at once. It is computationally super cheap. It takes just a millisecond to find best fit parameters. It will be useful in future missions like Plato, where we are expected to observe more than 100,000 stars. So how does this machine learning work? So we feed in the power spectrum into a trained neural network, and it outputs all the global seismic parameters. For example, large frequency separation delta nu, nu max, and delta pi, etc. To do this, it requires a large realistic training data set. And to construct this large realistic training data set, we have used simulations. We have used simulations to produce this data set. The advantage with the simulations is that we can produce as many as we like. In this context, we have produced millions of simulations to train our neural network. And the challenging part of the simulations is that they need to be realistic. Because we are not using the real data or Kepler data, the simulations need to be realistic. Now, I will describe the simulations in my next slide. So to show the quality for our simulations, we have compared the power spectrum of a red giant star, and we have shown its various components using our simulation. Here in the bottom panel, you can see the red giant star's power spectrum. On the top panel, I have various parts of our simulation. You can see here L equal to 0, L equal to 2, and L equal to 3 P modes. These are given by this expression on the left-hand side. So you can see that all these modes are separated uniformly with a bit of curvature. So this is regarding P modes. And the heights and widths of these P modes depend on various factors. It depends on the SNR of the star. It depends on the heights and widths of L equal to 2 and L equal to 3 modes depend on the visibility of these modes. It depends on their associated L equal to 0 modes height and width. We have constructed L equal to the mode heights of L equal to 0 modes and L equal mainly using a template, red giant template. So this is regarding P modes. There are also mixed modes in this power spectrum. As I said, as the star evolves, we can observe these mixed modes. The mixed modes are given by the solution of this implicit equation, which is shown on the left-hand side, where Q is the coupling constant and delta pi is the large period separation. Nu P and nu G are respective P and G modes frequency. Now, and nu G is given by this equation. The heights and widths of this mixed mode depend on the contribution of individual P and G mode inertia within that mixed mode. This assumption is formulated in Benemer et al. 2014. This is with respect to mixed modes. And combining this P modes and mixed modes, the simulation looks something like this. You can see that it is already simulating this power spectrum good enough, but there are also more effects. There's effect of rotation. Rotation breaks the spherical symmetry of the star and lifts the degeneracy of these modes in azimuthal quantum number m. Each mode of degree L is split into 2L plus 1 components. And the splitting of each mode depends on the rate of rotation rates of envelope and core. It also depends on the contribution of individual P and G mode inertia within that mixed mode. So you can see that these modes are symmetrically split. This is the assumption, and you can see that with each L equal to 1 mixed mode, there are two neighboring M equal to -1 and M equal to +1 modes, which are rotationally split symmetrically. Now, we have assumed a two-zone model. We have envelope rotation rate and core rotation rate to calculate this splitting. And then we also have effect of inclination angle. Inclination angle changes the relative amplitude of each individual M mode. It is formulated in Gison 2003. And we have used this expression to calculate the amplitude of each M component. You can see that at inclination angle of 0 degrees, we can observe this M equal to 0 mode, but we can't observe M equal to -1 and M equal to +1 component. At inclination angle of 90 degrees, we can't really see M equal to 0 mode. And at inclination angle of approximately 54 degrees, all these three modes have more or less equal amplitudes. We have considered this effect into our simulation. And now considering all these effects, this is how the simulation looks like. This is how our simulation looks like. You can see that the simulation matches the data really well. It mimics the data really well. And so these are L equal to 0 modes, L equal to 2 modes, and there are L equal to 1 mixed modes here. The heights are also matching and the frequencies are also matching really well. Now, the simulation is basically constructed using seismology, and it has all these various seismic parameters. all these seismic parameters are connected to the physical parameters of the star. For example, delta nu is related to the envelope size of the star. Delta pi is related to core size of the star. Q is related to size of the evanescent zone, thickness of the evanescent zone of the star. And the splitting is directly related to the core rotation rate and envelope rotation rate, and also the inclination angle of the star, which modifies the amplitudes of these M components. Now we have shown that our simulations work really nice, and so we have generated millions such simulations to train our machine. After training the machine, here's the magic. We just feed in the power spectrum, and it outputs all the posterior distributions of these seismic parameters. The brown line, brown dashed line, that shows the true value of the simulation. Here we feed in the noise plus simulation, the real star of this KIC, and we feed into the machine, and it outputs all these posteriors of different seismic parameters. And you can see that all these posteriors are getting back, recovering the true value of the simulation very well. So this is only for one star, right? This is only for one particular red giant. Now I will show you the result on an ensemble of stars. I will show you result on this 3000 stars. So here I will show you the measurements. I'm plotting the measurements of the seismic parameters that are inferred from machine and comparing it with the published values that are previously reported. You can see that all the measurements of delta nu are agreeing with the published values of delta nu, leaving out a few stars. For greater than 90% of the stars, the difference between the published values and the measurements here are less than 1.5%. And similarly for the nu max, we can see that the delta nu and nu max agree at all stages of evolution from subgiant to red giant. Subgiants, these are subgiants, and these are red giants and red clumps. So our inference agrees with the published values across the stages. Again, nu max as well. For greater than 90% of the stars, the difference in measurements here and the published values are less than 5%. Similarly, for delta pi, you can see that we can infer delta pi very successfully in many stars. For greater than 90% of the stars, the difference in measurements here and the published values of delta pi is less than 8%. So this result in particular validates two things. It validates our simulations, it validates our machine. We haven't used any real data in our simulations, but still we can measure these seismic parameters on these real stars, Kepler stars of 3000 Kepler stars. Now, so far it's only about measurement. Now I'll talk about something about physics of these that can be inferred from these observations. So as I promised, the first result, machine recovering the existing observation. Now here, if we take the delta pi measurements from the machine and delta nu measurements from the machine, we can, on this Kepler data of 3000 stars, we can see that there are two groups, red giants and clumps. We haven't actually fed in this distribution, right? We have fed in distribution something like this. In the training data set, the distribution is something like this. It is uniform across in delta nu, delta pi space. But and also in training, in simulation, we can the machine is working accurately on simulation. It can infer delta nu and delta pi on simulation. When it is applied on real data, the distribution is something like this. So it is independently recovering this distribution on Kepler data. And we can see these two groups, red giants and clumps, that can be separated, well separated in this delta pi delta nu diagram. And so if we see these red giants, they have a linear relationship between delta pi and delta nu. And we know that the envelope size of the star is inversely proportional to delta nu, and core size of the star is proportional to delta pi approximately. So what does it say? It says that the core contracts as envelope expands. Although this is already known, this is independently discovered from the machine. Now I'll talk about something else. I'll talk about, this is for delta nu and delta pi. Similarly, we can see other distributions. Now I'll talk about Q and delta nu, Q versus delta nu. Again, machine can infer Q, machine can infer delta nu. When we see the distribution of this Q and delta nu, we can, it's something like this. So if we look at red giants again, so again, I just want to emphasize one point here. This distribution hasn't been taught particularly. It is independently recovered in the Kepler dataset. In the training dataset, the distribution looks something like this. And in the Kepler data, the distribution is something like this. So it is completely recovered by the machine independently. And the point I want to make here is, this has been observed previously, but we observe a stronger slope, like a greater slope. So this is the previous trend of Q versus delta nu. Here, what we are doing is just collecting some stars of in the delta nu space, in that similar delta nu space, and we are averaging the Q and delta nu in that space. Okay. Now, if you see this, this is the previous trend, and the green points show the trends obtained from the machine. You can see there's a stronger or a greater slope here. What does it mean? That the evanescent zones are larger than expected, and the rate of expansion is greater than previously believed. So why do you have to believe this result, right? This is obtained from the machine. Why do you have to believe this result? I'll present some evidence. This is the evidence one. Yes. So if you see here, I'm taking a particular star where the reported value, previously reported value was 0.11. And here I'm comparing the SL diagrams of that particular star with our simulation. You can see that as Q increases, the L equal to 1 visible mixed modes increase. I'll play the simulation again. You can see that as the Q increases, the visible L equal to 1 mixed modes increase. So when we compare the SL diagrams of the star and of the simulation with a 0.03 and a simulation with Q of 0.11, you can see that the star's SL diagram is closer to the SL diagram of Q equals to 0.03. This is one evidence. We also have done MCMC analysis on the star. You can see the data in black and the MCMC fit in red. The fit represents the data really well. And across all modes, L equal to 0, L equal to 1, and L equal to 2 modes. And here's the SL diagram of that particular star and SL diagram of the simulation. You can see that the fit is really nice. and it matches the data really well. And this is a posterior distribution that has been obtained from MCMC and the machine. Both are agreeing. The black line shows the machine and the green dashed line shows the MCMC distribution. Both are agreeing with each other. To make another point, here I've started the MCMC inference with a very large value, 0.11, but it converges to a lower value of 0.03, which is obtained from the machine. So this MCMC, and which is completely independent technique, also supports the measurements obtained from the machine. So what does it say? When we compare it with the theory again, here is how it looks. You can see in the Q versus delta nu, the blue points represent the data, and the green curve shows the theoretical values of Q for a stellar model. You can see that as delta nu decreases, Q decreases and agrees with this data. And here is the same data, but plotted with each delta nu bin and taken an average value of Q. And I just want to point that the data agrees with the theory. So what does it say? It says that evanescent zones are larger than previous theory. Okay. Now we have, in this analysis, we also encountered something interesting. If we see period spacing measurements in these stars with low coupling constant, it's something interesting. So if you see this period spacing inference obtained from MCMC and as well as the machine, you can see the machine distribution is almost flat, and MCMC is not converging to a single value, not a single value of delta pi. This is something which we didn't understand initially, but we have also seen some other stars like this. For example, here's one more star. I'm comparing two stars in particular, where coupling constant is 0.15 and coupling constant is less than 0.05. And you can see the inferences of delta pi obtained by the machine in both these cases. You can see the certainty in the delta pi's measurement with a higher coupling constant, star with a higher coupling constant, and star with a lower coupling constant. You can see that the uncertainty is very, very low in stars with a higher coupling constant, whereas stars with a lower coupling constant have a very bad uncertainty, very bad certainty. So here's one important study that we have seen, that relative uncertainty in delta pi is decreasing with increasing Q. So this is something that we can also expect it theoretically. From the implicit mixed mode equation, if Q tends to 0, then all the any value of delta pi satisfies this equation. So we can't really infer delta pi at very low values of Q, which has been independently confirmed from the data. And also, if Q is really low, the evanescent zone is thicker. So the modes completely decay in the or decay a lot in the evanescent zone, and the information about the core is a lot less compared to when Q is higher or evanescent zone is thinner. So this is regarding this delta pi measurements and this in these stars with lower coupling constant. Now, as I've shown so far, I've talked about machine recovering existing studies, machine discovering something deviating from existing studies. Now I'll talk about something new, machine discovering some new observation. So I'm sorry, I'll be only showing the preliminary result and an approximate plot. Here is a plot of rotation rate versus delta nu. Again, we didn't incorporate any such bias or any such, we have only incorporated uniform distribution in delta nu and omega space, but it independently recovers something like this on the Kepler data. So what I want to say is that, yes, we have seen a similar studies previously that the co-rotation is more or less 1 to 2 microhertz or 0.5 to 2 microhertz in red giants. Here, red dots represent the red giant stars and brown dots represent the red clump stars. What we have seen is, although there are the co-rotation in clump phase decreases, we have seen something strange, like there are few stars with rapidly rotating core in the clump phase. This is something completely new. We are writing a paper about this. This is something where, which the current models can't explain. So why do you have to again believe this, right? So I have some partial evidence to show. You can see the core rotation measured by the machine versus core rotation already measured and published in 350 stars. We can see that the core rotation values between measurements and the published values, this is in red giant phase, they agree more or less. Most of the stars are in 1:1 ratio with that particular rotation rate. And there are this 1:2 and 2:1 branch. These stars are because of inclination angle and core rotation rate degeneracy. And yeah, so this is a partial evidence that supports the faster rotating clumps. And this is something only in the core rotation rate. Now, I will also talk about the envelope rotation rate that is directly only inferred from seismology, astroseismic observations. We haven't used any other data. So what we have seen is, if we take the ratio of the envelope rotation rate inferred from the machine and core rotation rate inferred from the machine, we can see that there is a sharp transition when the star travels from red giant phase to red clump phase. We can see a sharp transition somewhere here. Although this is expected theoretically that the envelope rotation rate increases. This is taken from Fuller et al. 2019. And envelope rotation rate, increase in envelope rotation rate and decrease in core rotation rate in the clump phase. This is something strange which we have observed. We have observed some stars having envelope rotating faster than cores. This is something new which we have observed. So we are working with Dr. Jim Fuller on formulating the theory to explain these observations. And this is regarding rotation. And now I have a final new result on structure of these red giants. So when we look at this delta pi delta nu diagram, in the previous study, what we have observed is a limited number of stars. But here I have analyzed the full catalog of 21,000 stars. And when we have analyzed this full catalog and we take these measurements and study this correlation, what we are seeing is there's this new branch and delta pi delta nu space, which is previously not been observed. And but there is some theory by Sebastian D'Hauvels that explains this branch. Although this is, we have to do a more careful study on this particular new branch. So Sebastian D'Hauvels has proposed that non-degenerate cores can have a larger delta pi at same values of delta nu. So this could be in principle non-degenerate cores, but there are also other speculations like the scaling relations could be incorrect or could not be applied for these stars. these are only 30 to 40 stars or 50 stars at max, and out of 21,000 stars, which we have seen. But they clearly show a new branch. So this is again a new result from which has been obtained from the machine. So to summarize, deep learning has been successful in seismology of red giants. AI proves the existing result of core contraction and envelope expansion. We expect evanescent zones to be larger, and these measurements are consistent with the theory. We identify a new evolution of core rotation and we have discovered some fast clump rotators. We find a direct evidence of angular momentum transport, and we have observed stars where envelope rotation rate is faster than core rotation rate. And we probably have some non-degenerate red giant cores and a new branch in delta pi delta nu space. Thank you.
Okay, thank you very much, Siddharth. So it's time for question. Could you, if you have questions? Okay, Rafa, please go ahead.
Hi, so I don't put my camera because I am just in a bad configuration with the light. So thank you very much for the presentation. It was really nice result that you have. I have two fast questions. The first one is concerning the last part when you compare the rotation of the core with the surface, because you showed at the beginning that the posterior probability of the surface or the envelope rotation was not a Gaussian. It was at the very beginning when you showed the posterior probabilities of most of the parameters. I recall that the posterior of the envelope was, yeah, that one, was all but a Gaussian. So at what
extent? This is for this particular star, KIC 6191190, but we have 21,000 stars. We have studied all these stars, and each star will have its own distribution.
Yeah, sure.
So, yes. So when we take those distributions, we can get the median and we can get some standard deviation from the distribution. And that's what we have plotted here. We have plotted the medians of these, or this is an approximate plot. Just to give context, it is medians. And so what we did is we've taken the ratio of two medians, the median value of envelope rotation rate and median value of core rotation rate. And the ratio is this.
Okay, so that explains. And I have a second, probably a little naive question. Have you plotted the inclination angles you obtain?
So we haven't compared to any existing study. Yes, we have inclination angles of each of these stars.
And do you have a uniform distribution, or any?
No, it is not. It is not uniform distribution. It is proportional to sin A or something like that. Yeah.
Okay, so it's what we expect, that we have a completely random
isotropic distribution.
Okay, that was my question. Thank you very much.
Thank you.
Okay, so the next question is by Dennis Sterol.
Hello, thank you for a great talk. As you can imagine, I'm quite interested in that. So my question is, I didn't quite get one part of how you made the simulations. Do you, for each set of input parameters of your simulations, do you then on top of that make multiple versions of it by adding chi-square noise?
So we haven't, yes, we can do that, but what we did is we have taken multiple combinations of various combinations of delta nu, delta pi, q, omega core, omega envelope, inclination angle, and several other parameters. And we have million combinations of this parameter space. And for each set of parameters, we have made a simulation. And then we have added noise on top of the simulation, which is described by Harvey profile and white noise.
Okay. So one other thing, the odd stars that you're pointing out that you're finding, have you considered merger products or mass transfer to be the result of those weird stars you have seen in those last plots?
In the rotation case?
So rotation was one of them, but I think there was another one. Yeah, so that one, and that one. So both those plots show stars in unusual positions. And so obviously single star evolution, it seems unlikely, but did you consider and also the second branch stars, could that be something from, binarity or more exotic?
So second branch, it is not clear. What we are speculating is that these could be non-degenerate cores. The other thing we are speculating is that the scaling relation may not be applied to these stars. But yes, to explain rotation, we are considering some merger models. We are working on it. So we are collaborating with Dr. Jim Fuller on this. Yes.
Okay, excellent. Thank you.
Okay, so the next question is by Savita.
Hi, thanks for a very interesting talk, a very, very nice work. I was just wondering, I think it's a bit related to what Dennis was asking. I was wondering how much your neural network was dependent on the signal to noise ratio for the Newmax and Delta Nu.
For Newmax and Delta Nu, you can see that it works really well, even if the SNR is really low, but it depends. If there is no signal, of course, it won't work. But what we get is uncertainty with each measurement. So we can get an idea of how good the inference is. So you can see on a 3000 stars from Kepler in this catalog, Mossa et al. 2014 and Brad et al. 2016, it's working really well, especially for Newmax and Delta Nu. Yes.
Yeah, but I guess in their sample didn't have too many of the very low signal to noise ratio. So I would be curious to
yes, but we did study for Newmax and Delta Nu even on, I remember we doing study on 16,000 stars as well, and it was working really nice. So it's agreeing with the published values.
Okay, nice. I had another question and I forgot. Well, yeah, I was just wondering about the other plot, which is the weird stars with the core envelope above 1.
Yes.
I mean, so I understand you're putting the medium value, but I guess you also have uncertainties, right? So because it's very close to the 1 value, so could it?
Yes. We have uncertainties on these measurements as well. This is an approximate plot to be. Yes. But
It could be below.
So the uncertainties are not very huge. It is clearly greater than 1. The sigma is it is certainly above 1. So even with uncertainty, yes.
But just slightly above 1, right? Because it's very.
So it is close to 1.3, I think. Yeah, 1.3. Yes.
Okay.
Yeah. But it's not expected from the theory, right? That is something.
Yeah. Thanks.
Okay, another question by Rafa.
Yeah, it's going in the same direction than Savita. So I guess, and probably the answer is yes or no. When you train but if you find some noise, is my rabbit just running away all the time around. Sorry about that. So when you train your network, you didn't use any input on the resolution. Yes. I mean, the length of the time series, nor on the magnitude of the star.
We have considered the resolution effect as well. So what we did is we have changed the observation time and we fed in the interpolated data into the machine. So, yeah.
Okay. And for the magnitude of the star, which is what Savita was saying, the Snelson ratio, it's more or less fixed. It's not higher or lower. My question is, if you want to apply this, for example, to K2, you cannot apply directly, right? You should probably tweak the input data to shorter time series.
Yes. We have to do that, but we have simulations to do that, and we are planning to do that. Yes. So
yeah, it's just a matter of changing the inputs, but yeah, you have to do it. Okay, thank you very much.
Giovanni has a question in the chat. Why the approximate plots, by the way? So Giovanni, if you
Yeah.
can explain the question.
Yeah, sorry. Thank you for the very interesting talk. My question is about these approximate plots you're showing us.
Yes.
Why this format and not, you know, preliminary plots that?
Okay,
I don't
so these are, I'll present, we're writing this paper up, and so that is the reason, that is the only reason. So yeah, there's nothing else. So we will show, after submitting the paper, we can share the direct plots as well. So yeah.
Okay, that's the reason I suspected. I mean, okay.
Okay, so any other questions? May I ask one? You showed
sure.
some stars of faster rotating envelope than the core, right?
Yes.
So are those results consistent with previous results by Charlotte and others?
So previously there hasn't been such study of where envelope rotation is directly extracted from seismology, seismic measurements. I'm not aware. So we haven't compared the envelope rotation rates in particular. We compared the core rotation rates and they are agreeing. And what we are confirming is again with using an MCMC technique to measure this envelope rotation rate, and if they are agreeing with the machine measurements, and if that will be the validation. Okay.
Okay, I see. Thank you. Any other questions or comments? Okay. So if there's no more questions, let me say some words at the end. And unfortunately, this is the last seminar of the series because, as Rita said at the beginning, it's difficult to continue to the next season. But on behalf of the steering committee, I would like to thank all of you for joining and supporting this series. And let us close this whole series with big thanks to Rita, who has already left for the next meeting, unfortunately. So see you again at some time and some places. Thank you. Bye.
Bye. Thank you.
Bye.
Bye.
Thank you. Yes, bye.
Thank you.